Problem 30 talks about two investments. A that gives a return of per year 200 euros per year, which you invest continuously, and B where the income stream is a constant to be found e to the minus 0.02t euros per year. Investment A is put for 3 years and B for 5 years. And both of them are deposit income stream is continuously and the return is compounded continuously with a rate of 8%. So you have to find what is the constant K. So investment A is equals to B. Because they are in different timings, one is 3 years and the other one is 5 years, we cannot compare them in the future. So we compute now the present value of these two. We want the present value of A to be equal to the present value of B. So let's compute that. We know the present value of an income stream F is equals to the integral between 0 and the time of the stream e to the minus RT dt, where R is the interest rate. So in our case we have for A, so is present value of the first one is the integral from 0 to 3 of 200 e to the minus 0.08t dt. That's equals to 200 e to the minus 0.08t divided by minus 0.08 between 0 and 3. So that's equals to 201 minus a to the minus 0.24 divided by 0.08. For the second stream, we have is the integral from 0 to 5 of the constant e to the minus 0.02 t, that's the function, and then e to the minus 0.08, that's the interest, dt. So we put together the exponentials is a constant outside, the integral from 0 to 5 of e to the minus 0.1 t dt. So it becomes k e to the minus 0.1 t minus 0.1 in the denominator between 0 and 5. And that's equals to k 1 minus a to the minus 0.5 divided by 0.1. And now we want these two streams to be equal. These two present values. So we want 200, 1 minus e to the minus 0.24 over 0.08 to be equals to k. And let me put this properly here. 5 k to 1 minus e to the minus 0.5 divided by 0.1, from which we got k is equal to 200 times 0.1 divided by 0.08, and then in the denominator 1 minus e to the minus 0.24, and here 1 minus c to the minus 0.5, and that's equal to 135.57. To solve this differential equation, well, because they're some kind of division, there's a fraction on the right hand side, it's not linear, it's a separable variables. So what we do is we write as usual y prime as dy over dx equals to minus y over x. Now we separate the variables. 1 over y dy equals minus 1 over x dx, and integrate both sides. Now after this we put the integral of this equal to the integral of this. Okay, so we have ln of absolute value of y equals minus ln of absolute value of x plus c. How much is c equals to? For that we use our initial conditions. The way initial conditions are written, you understand that y is a function of x. So that means for x equals to 1, y is equals to 1. So if we plug everything, log of 1 equals minus log of 1 plus c. A log of 1 is 0. So 0 is equal to 0 plus c, or c equals to 0, and ln y equals minus ln x. what have I taken out the absolute value? Well, because y at the beginning, x equals to 1, which is positive, and so is y. So this works near this point. The solution of this happens to be near. So we can assume that x and y are positive and remove the absolute value. It looks very ugly, so let's do an exponentiation. E to the ln y equals e to the minus ln x, which is 1 over e to the ln x. And now we know from mathematics, we know that the log, ln x, and the exponential are inverse functions. So this means what one function does, the other one undoes. So e to the ln x here is y, sorry, is equals to y, and this is 1 over x. And that's the solution. Again, we're in a problem of separation of variables. Let's put the y, this y here goes to the other side dividing, and this term here also goes to the side dividing, both of them. So we have x divided by x squared plus 4 dx equals 1 over y dy. And now we integrate both sides. The right one is easy, 1 over y dy is nothing but the log of absolute value of y. Left hand side we have the integral of x squared plus 4 x dx. Now the derivative of this, if this is w, the derivative of this is 2x. So we have to put a 2 here, and we put a 1/2 outside. And what we have is, this is equals to 1/2, and now we have the integral of w prime over w, so this is 1/2 log of actual value of x squared plus 4 plus c. Plus c, this is outside, so let's write it properly, c plus 1/2, and x squared plus 4 is 4 bigger, it's always positive, so here we can certainly forget the absolute value. Thus we have the log of absolute value of y is equal to c plus 1/2 the log of x squared plus 4. And now again we use our initial conditions. We say when x equals 0, y is equals to 1. So the log of 1, which we know is 0, is c plus 1/2 log of 4. So from which this is 0, we have 0 equals c plus 1/2 log of 4. So c equals minus 1/2 log of 4. But let's write this in a different way. This is minus 1/2 log of 2 squared. By the properties of the log, we know that the log of a to the n is equals to n times log of a. So what we have here, we have this is equals to minus 1/2, and this 2 comes out log of 2, so it's minus log of 2. And now we put all together, and what we have is that the log of y, and since y is equals to 1 is positive, is equals to the constant minus log of 2 plus 1/2 log of x squared plus 4. And we exponentiate both sides, and we know e to the log of y is equals to y. So here we have y is equals e to the minus ln 2 plus 1/2 ln x squared plus 4. Okay, let's operate this a little bit. First of all, we'll split e to the minus ln 2 times e to the 1/2 ln x squared plus 4. And we're going to use several properties. Let me put in a different color. Here we put in green. What do we have? First of all, e to the minus ln 2 is 1 over e to the ln 2, so that's 1/2. And now 1/2 the log of x squared plus 4, the 1/2 can go inside the log as a power. So this is the log of x squared plus 4 to the 1/2, or the log of root x squared plus 4. So now we are ready to go back to put our solution. Here we have y is equal to this thing here, which comes from here, 1/2, and this thing here comes from here. E to the log is nothing but x squared plus 4 square root, or x squared plus 4 divided by 2. And let's check when x is 0. This is only checking. You actually don't need to do it. So let's check. Here there's a check. X equals to 0, y is equal, so 0 plus 4 divided by 2, the square root of 4 by 2, 2 by 2, which is 1. Fine. This is a linear equation of degree 1. You can do like I showed you in class, it's homogeneous, so really you can do by separation of variables or by linear method. So let's look at the linear method, which is the characteristic polynomial is 2 lambda plus 1 equals to 0, lambda equals to minus 1/2. From there we have the fundamental solution, so is e to the minus x divided by 2, it's minus 1/2 of x. And the general solution is a combination of this, but it's a constant, e to the minus x over 2. Now we have here is homogeneous, no independent factor there, so that's the solution. And the only thing we have to do is use the initial conditions. So the initial condition is when x is 0, y is 1. So 1 is c, e to the 0, e to the 0 is 1, so c. So c is equals to 1, and from all that we have y is equals e to the minus x by 2. Now we have a linear equation of degree 2. We start, but again it's a homogeneous equation, so it's easy. Characteristic polynomial, lambda squared minus lambda minus 2 equals to 0. The roots of these are minus 1 and 2. And now we go to the fundamental solutions. So the fundamental solutions are e to the minus x by 2 and e to the 2x. And then we go to the general solution. The general solution will be a constant e to the minus x by 2 plus another constant e to the 2x. Since it's homogeneous, we can go directly for the initial conditions. But the initial conditions are the value at 0, which is easy, and the value of the derivative. So to use the initial conditions, we need to compute the derivative of this. The exponent comes down, so it's minus c1 over 2 e to the minus x by 2 plus 2 times c2 e to the 2x. So let's go. When x equals to 0, y is equals to 0. So we have to use this one here. 0 is c1 plus c2 because c to the 0 is 1. And when x equals to 0, y prime is equals to 3. So now we use this one. And then 3 is equals minus c1 over 2 plus 2 c2. That we have to solve this system. c1 plus c2 equals to 0, and 2c2 minus c1 by 2 is equals to 3. And from here, what do we have? So c1 is equals to minus c2. So 2c2 plus c2 over 2. c1 equals minus c2 is equals to 3. So this is 5 halves of c2 is equals to 3. So c2 is equals to 6 fifths. And c1 equals minus 6 over 5. And the answer is minus 6 over 5 e to the minus x by 2 plus 6 over 5 e to the 2x. This is again a linear equation of degree 2, non-homogeneous, because we have our. Be careful, the degree, the order of the highest derivative is 2 because we have a second derivative. So the characteristic polynomial is lambda squared plus 2 lambda equals to 0. Okay, to solve this, just take common factor lambda, lambda plus 2 equals to 0. So we got lambda equals to 0 and lambda equals to minus 2. So from here, the fundamental solutions are e to the 0 times x, which is e to the 0, which is 1, and e to the minus 2x. y1 is equals to 1, and y2 is e to the minus 2x. And the general solution? So the general solution will be, for the homogeneous part, that's what I put h here, this h is for homogeneous, will be a constant times 1 plus another constant e to the minus 2x, or constant plus plus another constant e to the minus 2x. Now this is a non-homogeneous equations, we have to look at the non-homogeneous part. The non-homogeneous part is constant 1, which should be written as a polynomial r of x, I'm using x as the, times e to the mu x. Okay, r of x is the number 1, so this is a polynomial of degree 0. And this, we don't see it, so this means mu is equal to 0, because e to the 0x is e to the 0, which is 1 also, okay? But when you don't see the exponential, it's because there is a mu equals to 0. So therefore, the particular solution of this will be another polynomial of the same x here, I'm using x. Another polynomial of the same degree, so this is a polynomial of degree 0, meaning a constant, e to the 0x, where we don't see it, and t to the k, where k is the number of times 0 has come out in the characteristic. But if you remember, one of the solutions of the characteristic is lambda equals to 0. So this is 1 because the number lambda equals to 0 appears once as a solution. So we have our particular is a constant to be found times t. Okay, the derivative of this is a, and the second derivative is 0. Pardon, it's not t but x. I keep doing the mistake of changing the variables. I call it x, ax. Doesn't matter. Now, this particular solution must satisfy that the second derivative plus 2 times the first derivative is 1. It has to satisfy why p is a solution of the equation. So this is equals to 1. So this means the second derivative, 0 plus 2 times a equals to 1. A is equals to 1/2. So we're almost done. What do we have? We have, if you remember, the general solution has to be homogeneous plus the particular. The homogeneous is C1 plus C2 e to the minus 2x plus this is the homogeneous. And here it says C1 plus the particular, which is 1/2 of x. This is the particular. And now we're going to use the initial conditions. The initial conditions involve a derivative, so let's compute the derivative of this. Y prime is, the derivative of C1 is 0, minus 2C2 e to the minus 2x, plus the derivative of 1/2 of x is 1/2. Okay, our initial condition says y of 0 equals to 0, so replacing here, we have that 0 is equals to C1 plus C2 plus 1/2 of 0. Doesn't count. And y prime of 0 is equals to 1. So y prime of 0 is equals to 1. So 1 is equal. Now we replace here. So this is 1 star. The other one is minus 2 times C2 plus 1/2 in the 2 stars. Okay? So we have to solve against C1 plus C2 equals to 0. And then move the minus the 1/2 to the other side. We have minus 2C2 equals to 1/2, from which C2 is equals to minus 1/4. And from here, C1 is equals to 1/4. And going back to the solution, we have y equals to C1 plus C2 e to the minus 2x plus 1/2 of x. And that's the answer to our problem. Linear differential equation of degree 1, non-homogeneous. Characteristic is lambda plus 1 equals to 0, or lambda equals to minus 1. Then fundamental solution, there is only one, so the general solution of the homogeneous solution part, homogeneous solution, yh is equal to a constant e to the minus x. Now let's go for the particular part. We have x. This has to be written as a polynomial e to the mu x. As we don't, the polynomial rx is a polynomial, is equal to x is the polynomial. So this is a polynomial of degree 1. And mu is equal to 0. Now, how many times is 0 a solution of the characteristic? None. So t to the k factor is t to the 0, because k is 0, so that's 1. It doesn't appear. So the particular will be simply a polynomial of degree 1. That's ax plus b. What is the derivative of this? Well, yp prime is a. And it must satisfy the equation. So we must have yp prime plus yp is equals to x. So that means a, which is yp prime, plus ax plus b has to be x. You can do this in many ways, but the obvious way to do it is ax, a is equals to 1, and then a plus b does not appear on the right hand side, a plus b is 0, b equals to minus 1. Okay, so we have the particular solution is a, which is 1, x plus b, which is minus 1. And the solution to the problem is the homogeneous plus the particular. So that's equals to homogeneous constant e to the minus x plus x minus 1. How do we find the value of the constant? For that we use the initial condition, which y of 0 is equals to 1. Initial condition, y of 0 equals to 1. By the way, the degree of the equation is the order of the highest derivative. In this case is 1. So if you observe, the characteristic equation is also degree 1. And the number of initial conditions is only one initial condition. All these are related. Okay, let's check. Y of 0 equals to 1. So 0 is equal to c e to the 0 plus 0 minus 1, c minus 1, c equals to 1, and y is equal to e to the minus x. Sorry, y of 0 is equals to 1. I have done a mistake here. This should be 1. Sorry. 1. So c minus 1 is equals to 1, c equals to 2, and therefore our solution is 2e to the minus x plus x minus 1. Let's do an exercise we never do. Let's check this is the correct solution. We have to check that y prime plus y is x, and we have to check y of 0 equals to 1. Okay, so y prime is equals minus 2e to the minus x plus 1. So y prime plus y is minus 2e to the minus x plus 1 plus 2e to the minus x plus x minus 1. And here, what do we have? So this guy cancels this guy, and the 1 cancels the 1. So we're left with x, exactly what we need, x. And then y of 0 is equals to, here, y of 0 is 2 times e to the 0 plus 0 minus 1, 2 minus 1, which is 1. So this is correct, this is correct. In this is the solution.